Okay, in this lecture, I'm going to have a little, I guess a little fun. We're going to talk about some different topologies of the line. We've already talked about one, which is sort of the real line, which will go on forever, with the standard topology, the usual topology, which is the topology of open intervals. And when I say the topology of open intervals, of course, I'm talking about the base of the topology are these open intervals. And we know that our arbitrary unions and arbitrary intersections of the base will generate the set that we will call the topology, say the Euclidean topology, how about that, for the real line. And then we talked about already an interesting topology of just the segment of the real line, and we called it the segment from 0 to 1. And I think, let's see, it was open, and the topology included the base of sets that went from 0 to 1 minus 1 over n. So there was a set that went from 0 to 1/2, from 0 to 1/3. I think when I first introduced it, I skipped this 1/3 for some reason. I don't know, that was a mistake because it belongs, and it's not 1/3, it's 2/3. And then 1 to 3/4, and then 1 at 4/5, and we talked about that topology. And I think that topology was called the nested interval topology. Nested interval topology. We could call that, say, TNE or NI, TNI, right? Now, we could talk about, by the way, the usual topology of the same interval, right? I could say, all right, forget the whole real line. Let's just take this open interval from 0 to 1 and introduce the standard topology on that. So we have two topologies for this interval. We have the standard topology and we have the nested interval topology. And what we could say is that this is we could name these things differently. We could say, well, this is the usual line, the usual line, and this could be the nested line, right? And so now I'm talking about some weird kind of line. Well, it's the nested line. Well, it's the same damn set. It's just got a different topology. And that makes the set very profoundly different when you treat it mathematically. So we have two types of line intervals here. Are there any other types of line intervals? So let's consider another type of line interval. And this type of line interval, it's called the closed interval topology. It's a little more convenient to divide this one, if I remember right, between 1 and -1. That's not a substantive difference, but it's a little easier to describe it that way. So there's 0 in the middle here. And in the closed interval topology, we include the two endpoints, right? That's one thing that we do differently. And then now that's the set, right? That's the set for which we need to define a topology on. Just like, you know, the interval from 0 to 1 was the set that the set that we need to define the topology on here. We need to define a topology for this set. Well, this set, the way we do that typically is we define the base. So what's the base going to be? Well, in this case, the base is going to be these closed intervals that begin from -1 and go to a point A with an open endpoint, and another set that starts at a B and goes to 1 with a closed endpoint. So this is a half open interval and a half open interval going from -1 to A and from B to 1. But there's a restriction. In this case, A must be greater than 0, and in this case, B must be less than 0. So that's very interesting because A will always be here and B will always be here. So in this closed interval topology, we will have, for example, if B is here, then that all sets where B is over here, all these half-open sets where B is over here, are part of the topology. And in this case, all of the sets where A is over on this side will be part of the topology. So we can have, if 0 is here, right? If that is a valid B, and this is a valid A, and this interval is a base of the topology, and this interval is a base of the topology. And what's important to understand, of course, is if you're a base of the topology, that means by definition you're an open set. So notice, these open sets, and this is just to make sure you don't get hung up on the words, they have a closed side, right? This is, in the terms of real analysis, this is a half open interval. But look, what we've said is, no, we're going to create a topology, and that topology we're going to call the closed interval topology, and that topology is going to have a bunch of open sets, and I'm defining these intervals here are part of the topology, and I just establish it. I say that that's the case. And despite the fact that they're half open intervals, they are open sets because they are members of the topology. And that's the definition of an open set. The open set is a member of the topology. The definition of a half open interval is loaded with information about whether or not something includes this point or not. And that's important. That's part of it. We're using that. But that doesn't mean it's not an open set. It's an open set because it's a member of the topology, and it's a member of the topology because we're putting it in there. The problem is when you put some sets in the member of a topology, you have to be able to include all of their unions and all of their intersections. So let's have a look at that. Let's look at the union question first. If I take the union of any two of these, what's going to happen? Well, the B is going to go from -1 to B, right? And B is always greater than 0, and the A is going to go from +1 down to A, where A is less than 0. And you'll notice the union of this is always going to include the entire set. So the union of any member of the base that involves A, well, I'll call that the lower member, and with any upper member. The union of any lower member of the base with any upper member of the base will always be the same thing, the real line. And it doesn't matter how close A is to 0. Since it's got to be less than 0 and B has got to be greater than 0, that union is always going to include the entire line. On the other hand, the union of any two of the upper elements of the base, right, and any two of those is always going to end up looking something like this. One value of B here, and then one value of B there, right, where 0 is here. Oops. What am I doing? Got that wrong, right? I got that backwards. Sorry. 0 is here, right? There's the line. And -1. So there will be one value of B here and one value of B here, right? And the union of those two, since it's this interval here, union with that interval there, it's always going to be the larger value of B. And likewise, it'll always be the smaller value of A. But there's no doubt that the larger value of B is already a member of the topology, because the larger value of B is just another interval of this form. So all the unions work out just fine. What about the intersections? The intersections are fun because the intersection of one of the upper elements with one of the lower elements is just going to be the open interval, an open interval between A and B. And I got to be careful. It's open for two reasons. It's open in the real, in the sense of real analysis, right? It's open because it doesn't include its endpoint. But the more relevant point about it being open is it is the intersection of two members of the base. The definition of a base is that all of its intersections and all of its unions are going to be open sets. So Well, the definition of a base is all of its intersections will be open sets. The definition of open sets is that all their unions and their intersections are going to be open sets. And so these definitions overlap a lot. But this open interval here is open. So look at the language. This open interval is open. Don't let that confuse you. I'm just saying the intersection of an upper element and a lower element of the base produces this interval. Because it's an intersection, we have to make sure it's included in the set. And that's it. All you can do is those things, right? All you can do is take intersection. If it's a base, all you can do is take intersections and unions to find all the elements of the topology. So all the elements of the topology include elements of this type, elements of this type, the entire line itself, of course. So I guess I should write that in there, right? This is part of the topology. The null set is part of the topology, and that's always true, right? This isn't true because this is not true. This is not a member of the topology just because it's the union of any two of these two types of bases. The entire set is always an element of the topology. So that's actually this is an element of the topology for two separate reasons, right? This has always got to be added into the topology. And then lastly, open intervals that look like A, B are members. But remember, these aren't just every open interval. It must include 0, right? Must include 0. So, and that's just the way this is all structured, right? 0 is always going to be inside that. So that's not any open interval, right? That's not that we haven't reproduced the usual line using this base. We have not, because we don't allow every open interval to be an open set. Only the open intervals that contain 0 are open sets. All right, so that's the third topology that we've learned. Let's see, is there another one? Of course there is. Let me do some, let's see. So we'll talk about one other topology. This one is called, we'll call it the Co-finite topology. And I am going to draw it. It'll also be on a segment of the line. Again, the segments really don't matter where they start and where they end, but let's just do this one from 0 to 1. 0 to 1 seems to be the easiest. The only reason we used -1 to +1 in the last time was because it's kind of convenient to have 0 to be the point in the middle. It just sort of makes the story a little easier, I think. But the co-finite topology is actually a very curious one. But the way it works is you first of all, this is the set. The set is the set of all points from 0 to 1. And then you pick a finite number of points. Pick a finite number of points, like say 3 points, like this. And then what you do is you take all of the points in the set except those 3 points. So you would basically be creating open intervals like this, right? You'd be creating open intervals like this, and the open set is the union of these open intervals. So the open set is basically all the points on the line except the ones you picked out. Sort of the way to think about it is you pick a bunch of points between 0 and 1, right? Say those two, and then the open set is the complement of those 2 points, right? So the open, and that's exactly what this is. This stuff here is the complement of the set of those 3 points. So if I called, maybe it's clear, if I called that point A, and that point B, and that point C, I can form the set A, B, C, right? And I call that set, say, S. Well, the complement of S, which is, I think SC is a typical notation for the complement. I think S bar is always the closure of a set, and I think SC is the complement of a set. So the complement of the set, so SC is an element of the co-finite topology, CF. So we have 3 different topologies. Now you can see, I guess we have to check, right? Are all the unions of every possible open set also open? Well, it might be easier to look at it from a simpler perspective, right? If we just pick, say, 1 point. So this is the open set of the co-finite topology where we just use the point A, and then if I do it at a point B, right, I get this set. And what's the union of those two sets? Well, the union of those two sets is the whole line, right? So, and again, we're in a situation as we were with this previous topology we did. This one here, the closed interval topology had the same issue, right? The union of, there were two open sets, then the union of them produced the whole line. Well, that's the same thing here. Any two of these are going to produce the whole line. There is the possibility, however, that I could have taken an open set like this, where I chose A here, and then another one where I chose A again, but I also chose B, right? So the union of those two sets is going to be A, right? It's going to be the same cofinite one as the original. In other words, if the union of this, if I duplicate the point and take the union with the duplicate, then that point is out, but that's already an open set by definition because we are including, that's how we defined, we've already put these in the topology. We've already included sets of the way I've defined them in the topology, so the union here is still in the topology. So all the unions are going to be in the topology. How about all of the intersections? So what would an intersection look like between these kinds of sets? Well, let's just consider this one here, right? The intersection of A and B would be, well, this interval is intersected. This is not an intersection because A isn't in B, so we would lose that point. This is part of the intersection, but B is not in A. So basically, the intersection is going to be the cofinite interval, or the cofinite union of all of the omitted points in both of the sets. So the intersection of these two sets is just going to be like this, A and B. So you basically take all of the omitted points and you put them in one collection. But there's no limit to how many points you're allowed to omit in this. I could omit 100, 100,000, 1,000,000. It's got to be a finite number, but I can omit any finite number of points. So this is already part of the topology just by the definition. We've already included all those sets. So all the intersections are in. So this is indeed a topology. If we make sure that we add the null set and the total set itself, which we already have. So all of these topologies are now available to us. In fact, let me just erase them all and go back, and we'll say we have the usual topology, T Euclidean, then we have the, what did I call this, the closed interval topology, T closed interval, where we were basically dealing with the zero. I'll just sort of symbolize it this way, A and B. We had the nested interval topology, right? We had that one, which went like this, where we had these things here at 1 over n. That was T nested interval. Then we had, which one did we just do? We just did the co-finite. T was the co-finite topology, and there's one other. I know one more. Oh, yes, there's one more. It's called the lower limit topology. The lower limit topology is really fascinating, but it's actually easy to explain. The lower limit topology just uses the base of the lower limit topology are the half-open intervals AB, right? In the Euclidean topology, the base is the intervals AB. In the lower limit topology, it's half-open, so B must be greater than A. And this has actually this topology is kind of famous. There's a guy, I forget his name, but we'll call this the lower limit topology. So there's multiple topologies of the line. Likewise, there's a couple topologies of the plane they're much harder to describe, so I think I'm just gonna pass on it. We have everything we need now to do an examination of the concept of separability. I mean, we want to see why these topologies matter, right? And separability is why these topologies matter. So the first thing we're going to talk about is something called T0 separability. And T0 separability has the following demand. I need to be able to take any 2 points in the set, and I need to be able to at least find an open set that contains one of the points and not the other. And that's it, right? That's the thing. I have to be able to distinguish this. You can see why we're separating. You're separating the notion of separability. The notion of separation means, can I find open sets that can distinguish between these 2 points, where distinguish means find different open sets that contain the points, and they're different. And how different are the open sets, and how many of these different open sets can we find? Actually, how many is not so much the problem, is just the different possibilities. And the different possibilities, the T0 is like the weakest one. I need to be able to take any 2 points in the set, and I should be able to find an open set, some open set that at least contains one of the points but not the other. And what's interesting is, if you look at the open interval, and if you use the Euclidean topology, this is not a problem, right? I pick any 2 points, and I just pick an interval that contains one of those points, and I've satisfied this. I have found an open set that contains one of the points and not the other. Therefore, the Euclidean line is T0. Now, it turns out there's other separability things that the Euclidean line is also, but it's definitely T0. So now, let's take a look at one of our other lines. Let's take a look at the nested line. Remember this? That was the one that went like this, 1/3 or 2/3, 3/4. So I'll only draw those. Now, if we look at this, and I say, okay, I'm going to put 1 point here. I'll call that the red point, and I'll call this other one the red point. And I have 2 red points. The question is am I allowed to call one of the points blue? The only way I could call 1 point red and the other blue is if I could distinguish them. Well, can I distinguish these points? And sure, because the distinguish means separate, and separate means open set. Well, I have an open set right here, right? This open set can separate this red point from that red point. Well, that's good. So I've now separated this red point from that red point, so I'm going to say that this is now a green point. Why not? Because I can separate it, I can call it something else. It's in its own, it's not in this open set here. On the other hand, if I took this red point with that red point, now I actually have a problem, because this red point, there's no open set left. There's no more open sets left that can separate these 2 points. I can't do this, right? Because the rule was 1 minus 1 over n in my construction of the base of this topology. This was T nested interval, right? My basis of this topology had 1 minus 1 over n, establishing the location of these upper ends of the intervals. Well, this is the first one, right? There is none down here. So given that there's none of them down there, I'm stuck. I'm stuck with keeping both of these points in their same open set. I cannot separate them. So T0 is violated here because I found 2 points that I cannot take one of them and put it in its own open set. So the nested interval topology is not even T0, right? It's not even T0. Now, to find a topology of the line, or to find one of our lines that is T0, let's go to the closed interval topology, right? Remember, that was the one that had 0 in the middle, and I had to pick an A and a B, and this interval is an element of the base, and this interval is an element of the base, and therefore, because of the rule about intersections, this open interval that contains 0 is an element of the base. So let's look at this thing. So I'm going to do a few possibilities, right? Well, the first possibility is, say, an arbitrary point on the left side. Well, an arbitrary point on the left side and say an arbitrary point on the right side. How about that? So I have these 2 points. Well, can I separate an arbitrary point on the left side from an arbitrary point on the right side? And sure, because if I select B such that B is here, right, the interval from A to B, that's an open set, and it contains this point, but it doesn't contain that point. And this, you can see, can be done for any 2 points that are on both sides of 0. So that's good. So I can always, if I have 2 points that are on both sides of 0, I can always sort of take advantage of the fact that I can create arbitrary intervals that include 0 and omit one of the points on one side, keep the point on the other side, and I can separate one point from another. In fact, I can do this symmetrically, right? I have the ability to let me do my 2 points. I can do this. I have the ability to separate the first red point from the second, but I also have the ability to separate the second red point from the first, right? This interval separates the second from the first. This one separates the point. So I can actually put, in this case, each one in its own open set, which is stronger than T0. T0 only insists that I can put one in its own open set. So this is actually stronger than T0. That condition, that little condition. Unfortunately, that doesn't cover all of the cases. And remember, for the separability rule to apply, it has to cover every case. So what's left? Well, let's look at this case. If I have 2 red points on one side of the line, right? Well, now what can I do here? Well, I can only work with B. I can put B right there, and I can separate one point from the other. But notice I cannot isolate each point into its own open set, but I can isolate the red point from the other red point. So I'm going to go ahead and allow myself to call this a blue point because I can separate the two. And I've put one in its own open set. And this, of course, works on the other side. If I had 2 blue points, I could always find an interval from the lower part of the base to separate the two and the upper part of the base to separate these two. So I'm good. I can actually put every point into its own open set. There's no other combinations. I either have 2 on this side, 2 on this side, or 1 on both sides. These I can separate, and I've just shown that we can separate these as well. So this is a T0 space. The nested one was not T0. This one is, in fact, T0. So the T closed interval topology is T0. Now, I've already sort of hinted at the next level of separability, which is called T1. And this, by the way, there's actual words for these. I think T1, I'm trying to remember, I think it's called a Frichet. God knows I'm not going to spell it right. You know, it's French. Frichet. I think T1 is called Frichet. I'm not even sure. T0 was like a Russian name with a K, I think. But either way, T1 is what we're after. So, but we've already kind of hinted at T1. We've hinted at it a little bit because what we talked about here was that in the well, not with the nested interval, with the closed interval topology, there were cases where we could separate one point from another, but we couldn't put each point in its own open set, right? In the Euclidean, we can always put each point in its own open set, like this, right? Where one point is in its open set and one point's in its open set. And this open set here does not contain this point, right? They're in 2 different open sets. And that's important, right? They're different open sets. So if they're in different open sets, the space is T1. And in the case of the closed interval topology, what we discovered is we could put a point in one open set, but we couldn't necessarily put the other point in its own open set. So that's why this is not T1. And that's the fun of this, right? We're showing spaces that are T0 but not T1, right? And we showed a space that's not even T0. We showed a space that's T0 but not T1. And now, and of course the Euclidean space is T0 and T1, right? Which makes perfect sense. So now we're kind of looking for a space that's just T1 and but not T2, right? Which we haven't gotten to. But I am going to show you, and that space is the co-finite topology, right? And the co-finite topology we're going to show is T1. Let me quickly do that. In fact, it's almost ridiculously easy for the co-finite topology, right? Because let's see, I just take a red point and a red point. My question is can I put each of those points in its own open set? And the answer is, well, look, I take that point there, and omit them, and then well, I don't want this red point in it because I want this red point in its own open set, so I choose that point, and then I create. Well, actually, I don't even need these 2 points, right? I don't even need those. In fact, I'm going to keep it simple. I'm just going to eliminate them. Draw the line. I just choose this point here, and I create this open set in the co-finite topology, which includes this red point, but it does not include that red point. And then I just flip the whole situation around, and I choose the point, the topology that omits that one, that omits this red point, but includes that red point. And boom, I've got it. This open set contains that red point, but not this one. And this open set contains this red point, but not that one. And so I have now separated these things into their own open sets, so I'm allowed to say, okay, I'm going to call that blue and that red. Because I have found open sets that contain one, but not the other. And therefore, the co-finite topology is T1, is for Shea. So it's the first, it's the other, aside from the Euclidean topology, which is certainly for Shea, the co-finite topology is, the co-finite topology is T0 and T1, right, of course. So now the question is, what's T2? So I will erase everything, and let's look at T2. The notion of being T2 is that not only can you take any 2 points and put them in their own open sets, but here's the kicker. The open sets have to be disjoint. And you see how that's much better, right? This circumstance is, according to topology, more highly separated than this circumstance. If all I can do is find open sets that they definitely isolate the points, but the open sets that are isolating the points aren't exactly isolated from each other. In this case, the open sets not only isolate the points, but the open sets are themselves isolated. And that's even better. That's even more separable. That's even finer. And you'll notice, by the way, the co-finite topology can never accomplish that. And that was why the co-finite topology is such a nice example, because it's actually hard to find a space that's T1 that isn't T2. But the co-finite topology is exactly that space, because if I'm trying to separate these 2 points, right, the set that does it, I omit the first one and I get that, and I omit the second one and I get that. Clearly these are the 2 open sets we just discussed, but it's very, very clear that there's tons of intersection between these 2 open sets. In fact, these 2 open sets are exactly the same set, except this one omits 1 point. This one here, this set here, omits that point and includes that point, and this one omits that point and includes that point. These sets literally differ by like a point. So they are almost identical sets. And they do in fact separate it because they are different open sets. These are not the same open sets, and they are both members of the topology. So they are open sets that separate the 2 points. But the intersection between these sets is huge, and they cannot be separated. But, lucky for us, of course, the Euclidean topology easily does this, right? Easily takes the red points, puts them in their own open intervals, and you can always do this so they're disjoint. There's no intersection. You can do it with an intersection, right? So, you know, sure, but the fact is these are disjoint. Oh, and by the way, the name for T2, that's the one name everybody does know, and it's Hausdorff. Hausdor. I think it's got 2 Fs. I've seen it spelled with 1 F, but I think it has 2 Fs. Anyway, Hausdorff, that's the big deal. And any decent space in the world, any space that we want to deal with, any topology that we want to work with in physics is almost always Hausdorff. The cases that aren't are cases that are unknown to me right now, but the point is you'll often see in mathematical treatments of physics, you'll often see, oh, well, we're studying manifolds, so we have to assume that we have a second countable Hausdorff space. And they assume that you know what that means because they assume that you understand your canonical topology math. And that's what they mean, second countable Hausdorff. Now, you can actually get stronger than Hausdorff. You can get stronger. You can have Hausdorff spaces that are regular and Hausdorff spaces that are normal, right? And now what you're talking about is you're talking about taking closed sets. You're replacing points with closed sets, and you're finding open sets that can separate closed sets from one another, right? If you can do that, or if you have a closed set and a point, can you at least separate a point from a closed set using disjoint open sets, right? Has to be disjoint open sets because that's what makes a space Hausdorff. I always forget which one of these is regular and which one is normal. I'm pretty sure this is regular and this is normal. This is normal. I'm going to go for the risk. If I'm wrong, I'm going to have to edit this. Regular. So now there is a topology of the plane that beautifully describes this. It's called the slotted disk topology. And it's a little too complicated to go in, but the slotted disk topology essentially takes the plane and separates it into 2 halves on both sides of a line. And on this half, you use the regular open disk topology, but none of the open sets are allowed to touch the line or cross the line. Likewise on this half. So you have open disk topology on this half and on this half. But on the line, but none of the disks are allowed to cross the line. So you have this weird problem with the line. But on the line, what you do is you take each point and you create a disk around the point, but then you exclude the other points in the line, right? So I would include the blue point, which is actually on the line, but I exclude these red points on the line. I should maybe draw this bigger. So I include the point on the line, and then I create a disk that goes around it, but it excludes the line itself, right? It's called a slotted disk. And the disk can be of any size, and it happens at every single point. Well, it turns out if you call those open sets, and then of course you call these open sets on both sides, and you take the union and intersection, everything is fine except on this line you actually end up having the discrete topology on the line. And look, by the time you're all done, you are abandoning normalness and or regularness. And so that's the kind of wacky stuff it takes to lose these properties. Okay, but having mentioned that, there is one important thing I'd like to add before we pause for today. That is the notion of the subspace topology. If I have a plane and I use the Euclidean plane, which means I have R squared, that's the set, and I have the Euclidean topology, And the Euclidean topology, of course, is this open ball topology. But now I have a line in this plane, and I just pull out the line. The line, I'll call that L. L is a subset of this R squared topology. L inherits its own topology. The intersection of every open set on the Euclidean plane with L, right, will induce a topology on L. And that topology will be the standard open Euclidean topology. And that's a very common property. You take a larger space, right, you cut out a subspace of that larger space, and you accept the induced topology on the subspace by the intersection of that subspace with all of the open sets of the topology. Very, very common. Another common topology is the Cartesian product topology. If I have a set X, well, that's a really bad choice here. If I have a set S and I take its Cartesian product with a set T, well, if S has its topology TS and T has its topology TT, then the Cartesian product, which is a set, has a topology TS cross TT. So you can also do that, and that's an important fact to know for topologies. Okay, anyway, I think we're done for today. We've covered some very interesting stuff. We've shown the separability axioms, and I've given I used some different topologies of the real line to illustrate them. The fact is there are lots of topologies out there that mathematicians have come up with. The slotted disk topology of the plane is an interesting one. You can look it up and read it. They're not hard to understand once you realize what's going on. They're just inventing open sets, putting them into the topology, showing that the union and intersection of those sets are all in the topology, and then they're kind of studying the different axioms. The next thing we need to talk about is countability, and we'll do that in our next lecture.